Welcome to the video homework for topic 4.12 and 13, dealing with the substituent effects on the regiochemistry of electrophilic aromatic substitution. Before you try this homework, I do recommend that you read lesson 4.12 and 4.13 in the Organic Chemistry 2 primer by Professors Tennyson, Hugeri, and Smith. Our first question is to provide at least one valid resonance structure for each major intermediate formed in the bromination of toluene. To address a problem like this, we have to first sketch out the particular process under consideration. In this lesson, we're talking specifically about the electrophilic aromatic substitution. So something like this might be your bromination conditions for toluene, and this is your structure of toluene. You might also use FeBr3. Now, more importantly, we're being asked to consider the major intermediates formed in the bromination of toluene. So we have to ask ourselves, well, what are the possible intermediates for all of the regioisomers you could form in an electrophilic aromatic substitution, in this case bromination? And we could get the ortho, meta, or para isomers. We should consider all the intermediates involved in potentially accessing those products. Now, since this is toluene modified with a methyl group represented by this R group here, we'll look at the representations of the mechanisms given in the primer lesson 4.12.2. And if we consider first the ortho addition, you can see all these different resonance contributors to the cation formed by the initial ortho substitution, ortho electrophilic addition. One thing I'd like to point out is that in the case of an ortho substitution, you will have a tertiary carbocation formed en route to the ortho addition product. Similarly, if we consider the substitution by some electrophile para to the R group, we'll get this initially formed carbocation, which has two additional resonance contributors, and one of which is a tertiary carbocation. Noticing that the tertiary carbocation is, of course, more stable than the secondary carbocations, so this has some additional stabilization. But when we have an electrophilic addition of your electrophile to a site that is meta to the already present substituent, we see that we have a secondary carbocation in each of the three possible resonance contributors. And because of this, the carbocation resulting from meta addition is less stable than those resulting from the ortho and para addition products. This is an important observation to answer this problem effectively because we are asked for the major intermediates. So we need to provide at least one valid resonance structure only for the major intermediates, which would be the more stable intermediates. So you'll have to provide one of the resonance contributors from the ortho route and at least one of the resonance structures from the intermediate resulting from the para addition. Our next question is a really common type of question for exams and quizzes in organic chemistry classes. Simply provide the major product of the reaction shown. And in order to effectively address this, you'll have to first say, well, if I see these conditions around the reaction arrow, what will I be adding to the benzene ring? What will change? And in this case, when you have sulfuric acid and nitric acid together, this will add a nitro group, and this reaction is called a nitration. Once we figure that out, we need to know what type of substituent is present so that we can figure out where the next substituent might add. In the current case, we know that a alkyl group, like the methyl group present on toluene, is an inductive donor. And with that in mind, we should be able to figure out which sites will be substituted. In the previous problem, we already went through all the possible carbocation intermediates that could form upon electrophilic addition, that's the first step of the nitration reaction, to toluene. And because of the added stability of the carbocation intermediates formed en route to the ortho and para products, those will be the sites that will be selectively substituted. So we should draw those out and look for any potential steric barriers to their formation. We see that both of these are pretty nice stable products. We should get a mixture of both the ortho and the para substituted products. Now here's another question of the same variety, just asking us to provide the major product. In this case, we start with nitrobenzene. And first we look at the conditions around the reaction arrow and say, well, what adds when we have these conditions? And these are the conditions for a chlorination reaction. And a chlorination reaction will simply add a chlorine. And now we have to figure out what type of substituent is present so that we know where on the ring, ortho, meta, or para to the nitro group, should we add that chlorine that we just figured out would add. Well, the nitro group is a resonance withdrawing group, and it's also an inductive withdrawing group, but resonance is a more powerful influence than is inductive force, so we focus on that. And now knowing that we have a resonance withdrawing group on the ring, we think, well, which sites will be substituted? And hopefully you'll recall from your reading in the primer that inductive or resonance strongly withdrawing groups like the nitro group are the only ones that are meta-directing substituents. So we should see meta-substitution, and the product would be the one in which you have the chloro group substituted meta to the nitro group. I should also point out that if you were to draw two products down and think that these were two different products, that would not be correct. Each of these is metachloronitrobenzene. You've just drawn one of these flipped over with respect to the other. These are actually two representations of the same compound. Now you might come across some of these provide the major product questions where whoever's asking the question of you is also trying to test a little bit of nomenclature. So instead of drawing a structure for you, they might say, well, what happens when anisole reacts under these conditions? So first we need to know, what is anisole? Well, anisole, hopefully you'll remember, is a benzene with a methoxy group on it. All right, so now that we figured that out, we can ask, well, what adds to that anisole under these reaction conditions? Personally, I find this condensed formula a little bit difficult to just envision in my head. It's a lot easier if I just draw out the line bond structure. So I've drawn that out there. And I know that when I have an alkyl chloride with aluminum trichloride, the aluminum trichloride will pull this chlorine off and leave you with a carbocation. Anytime you have a reaction where you have a carbocation, you should think about checking whether it's going to rearrange. And in this case, it will, from this primary to this tertiary site. And that will occur before anything else happens. So this is the unit that's actually going to be adding to the benzene ring. And now with all that information in place, we can finally say, well, now that we know what's going to add, what type of substituent is already there, because that's going to help us figure out where the substituent will add. Well, if we fill in these lone pairs on the oxygen of the methoxy group of anisole, we'll realize that this is a resonance donor. In introductory organic classes, generally you'll have a nitrogen with a lone pair or an oxygen with a lone pair that you'll see as your resonance donors. All right, so we know what type of substituent is present now. And that leads us to the question of which sites will be substituted. The resonance donors are ortho, para, directing groups. So we should have the potential for directing that tertiary butyl group. Remember the cation that we added looks like this. This carbon with a plus charge is the one that ends up attached to the benzene ring. So we could make the ortho product or the para product. But remember that one of the things we read about in the primer is that if you have this very sterically encumbering group with three branches, it's more difficult to place it beside an existing substituent than beside just a small hydrogen atom. So those tend to be disfavored when you have another potential substitution site. So in this case, your only major product will be the para-substituted product, the para-T-butyl anisole. Another type of question that's relatively common on these standardized exams and exams in organic chemistry classes are the ones where you have these aromatic rings that are hooked together, and you're asked to provide the major product for the different types of reactions. All right, so now you not only have to identify sites on one ring, but first decide which ring is going to react and then which sites on that ring will react. So our first reaction of this type is an iodination. And we have a lot of potential sites for the iodine to add. The molecule's symmetric here, but we have 1, 2, 3, 4 possible products. So we have to start off this problem the right way and first figure out what type of substituents are present. The chlorine is an inductive withdrawing group, slightly deactivating, whereas the oxygen of this OH group is a resonance donating group which activates the ring to electrophilic aromatic substitution. So which ring will react faster? Well, it's going to be the ring on the right. So the iodine that adds through this iodination process is going to add to some site on this ring. So ortho or meta to the OH group. Which sites will be activated? Well, we figured out that this is the activating substituent, and this group will activate sites ortho to it or para to it to subsequent reaction. These are the sites ortho to it, and they're equivalent to one another by symmetry. And this group here is para to the OH, but that group is blocked. There's no hydrogen to be substituted, so we don't consider that. So we should only get one possible product where the iodine substitutes ortho to the OH group. And here's a similar problem. And in this case, we're taking this two-ring system and subjecting it to these conditions. With a strong acid, and alcohol like ethanol will first protonate that oxygen. It will then be pulled off as water, and you'll be left with an ethyl cation. So we'll be adding an ethyl group to some site on one of the two rings. In order to figure out which ring is more active, we have to look at what types of substituents are present on the two rings. And we see a methyl group. It's an inductive donor. It can stabilize carbocation intermediates by hyperconjugation. We have a methoxy group like we saw in an earlier problem with anisole. This is a resonance donating group which helps activate a ring. And we've also seen the nitro group so far in this video homework, and we've identified that as a resonance withdrawing group. So we've deactivated this ring but activated this ring, so the ring on the left is going to be the one that gets substituted. It will react faster. So we've identified the correct ring. Which sites will be activated? Well, you have to use the directing ability of the most activating substituent. So we ignore this one, and we think only about the most activating resonance donor. Resonance is better at stabilizing cations, so that will dictate the next site of substitution. And these resonance donating substituents, as we learned in the primer, are ortho and para directing. So we would like to add the next substituent either ortho or para to this methoxy group. These are the sites that are ortho to it, but this one already has a methyl group on it. We don't have a hydrogen we can substitute. And ortho, meta, para to the methoxy is way up here. That's open for substitution, and so is this ortho site. We should be able to substitute either one of those. So we draw those out. Here's the ortho to the methoxy group site substituted. Here's the site para to the methoxy group substituted. And those two are both equally viable products.